This is the Math 4933 Math Major Seminar question about information transmission, error detection and correction for Wade Gerlich, Jackson Gregory, and Blaine McPhail Luttrell, due on April 3rd, 2020. The goal of this problem was for us to create a method to transmit data over a reliable channel but with potential interference and detect correct bit errors within the message caused by the interference efficiently. So why did we take the approach we ended up taking? So when we were presented with this problem, we first went and discussed if any of us had familiarity in this area. Having some background in computer information, we decided some check bits would be a good starting point for the discussion. Our idea is sending a string of check bits after the original message to find and correct errors. So we compute these check bits as the parity of the corresponding message bit and the preceding and succeeding bits of that bit, wrapping at the ends of the message from the start to the end and from the end to the start. Why is this method efficient? Well, first we need to define what it means for a detection or correction method to be efficient. So efficient in this case would be maximizing the amount of errors detected and corrected of the detected ones while keeping the check bit sequence as short as possible. And in our case, we focused on making sure that we had the most correction possible. We could have gone a little shorter with the same amount of detection, but with less correction. We opted for a 3-bit check system, as said before. So each bit within the check sequence will have a family of 3 bits to be compared to in the received message. So, the corresponding bit, the one before it, and the one after it, with the wrapping at the ends. And we found this to be the most efficient method because, as mentioned later, we examined both the 2 and 3-bit checks and found 3-bit check had a better detection rate and less overall problems with correction, while still having only needs to send n bits for an n-bit message, not any more, so it only doubles length. So here's some definitions. The parity of a set of bits is 0 if the sum of the bits is an even number, and 1 if the sum of the bits is an odd number. Transmission is an entire set of bits set through the channel and received by a recipient that sends a set of characters. We break this into the message and the check. The message of the transmission is a set of bits representing the set of characters that the sender is attempting to send to the receiver. In our method, it's the first half of the transmission. The check of the transmission is a set of bits used to detect and correct errors in the message, but it's not part of the original message. In our method, it's computed before sending the transmission and appended as the second half of the transmission. During our discussion of the problem, we had a few alternatives we considered. We considered a vector basis, considered different family sizes for the check bits, for example, 1 bit, and then another example we looked at 4-bit plus along those same lines. Now, for a vector basis, what we really found out is that what our method is pretty much a vector basis in and of itself, so we figured it was not really worth going off onto vector basis when we already had some of the power of that and just focus on the parity component. But a 1-bit check is not great because you're just sending the same message twice, and so then if you have an error in either the message or the check, you won't know which one had the error and which one was truly the original. So you can't correct anything, you can only detect, which is not what we want. And for 4-bit plus, we had the problem of too much overlap in our check bits. They were having to check too many of the original bits, which just caused some problems in the correction. Especially since computer messages are often multiples of 8 bits, because a byte is 8 bits. That means you're checking half of the thing with each bit, which is a lot. So we decided not to go with that. Stuck with 3. When a transmission is received, the recipient separates the received transmission into the message and the check as the first check for looking for errors. They then compute the check bits they would expect to receive for the message they received. If they're the same, you conclude no errors occurred, because it would require a minimum of 4 errors to get a valid message that was not the same as the initially sent message. But if the received check differs from the expected check by exactly 3 bits, n minus first, nth, and n plus first, you conclude that there was an error in the nth message bit that caused that. Correct that error, because it's much more likely you'll have a 1-bit error than 3 check bit errors. If the received check differs from the expected check by exactly 1 bit, the nth bit, you conclude that that nth check bit is the error, and you correct that, because it would require a lot of other errors to cause that exact one error. So if the received check differs by the expected check by a number of bits other than 1 or 3, errors can only be corrected if they can be split into disjoint occurrences of the previous two cases, which we'll discuss more in a couple slides. For example, the nth, n plus 4th, n plus 5th, and n plus 6th check bits differ. Since they do not have overlap, you could conclude the nth check bit had an error and the n plus 5th message bit had an error. But if, for example, the n minus 1st and n plus 1st check bits differ, it could be caused in multiple ways, and so you can only detect it, you cannot correct it. So now here's a theorem about the number of bits you can detect, and using our 3-bit parity check scheme, which uses n bits, any 1-bit error in a string or a transmission can be corrected. So here's the proof. If 1 bit is an error, it'll either be in the message or the check. First case, if it's in the message. Following our previously outlined method, you'll find the n minus 1st, nth, and n plus 1st check bits to differ, and so you will know that that nth bit can be corrected. Case 2, if the error is in the check, you'll find just that nth check bit is what differs from the expected, and so you will identify that as your error and correct it. So now the number of bits detectable in our 3-bit parity scheme, using n additional bits for the transmission for an n-bit message. Any 2-bit error in a string can be detected. 2 bits are an error, they can either overlap or be disjoint. If they overlap, for example, the nth and n plus 1st bit, or the nth and n plus 2nd bits, regardless of if those errors are message or check bits, they can both be in the message, both be in the check, or one be in each. The errors will overlap, and there will be at least 2 bits differing between the expected and received check bits. And since those differences can be created in multiple ways, you can only detect the error, not correct it. For example, if you receive the transmission in the left column, you'll see the check differs from the expected check by those 2 digits in the 3rd and 6th positions for this 8-bit message. And you'll see that there are 2 different possibilities that could cause this. Possibility 1, 2 bits in the message were in error, and possibility 2, 2 bits in the check were in error. So you have no way of knowing which one it is, so you must conclude that you have detected 2 errors, but you cannot correct them. But if the errors are disjoint, as we discussed before, if they do not overlap, can treat them as 2 instances of single errors, and they can be corrected using the correction algorithm. And since they've been corrected, they have, of course, been detected, because you have to detect an error in order to correct it. So, now, talking about the trade-offs for 2-bit versus 3-bit checks, because as we discussed earlier, a 1-bit or a 4-bit plus check both have disadvantages that make us not want to use them, but using a 2-bit parity check, where the check bits each check the corresponding message bit and either its preceding or succeeding bit, but not both as a 3-bit does, there is an argument to be made to do a 2-bit, so you have to check less bits per check bit, but we will discuss why we chose to go with the 3-bit. So our results found that the 2-bit parity check is more susceptible to falsely concluding that an error in the check bits was actually caused by an error in the message. It would only take 2 consecutive check bits to be wrong in a 2-bit sequence for the method to falsely conclude that the error was in the message rather than the check. Conversely, a 3-bit check would require 3 consecutive errors in the same manner to come to that false conclusion. Because, for example, if the nth and n plus 1st bits, check bits, were both wrong, you would conclude that since they are both looking at the n plus 1st message bit, that was the one in error, when in fact it could have been both of the check bits that were off, whereas in a 3-bit check you could detect that error, just not correct it, and it would take that 3rd check bit in a row being wrong in order to falsely conclude that the error came from the message rather than the check. So continuing off that, we would, as I said, only be able to detect that error, not correct it, in a 3-bit check, but it will not give you the false correction that you would have in a 2-bit where you think you can correct it, but you are actually causing it to be wrong. So the main trade-off is that the 2-bit check will fail, the 3-bit check can detect but not correct. So we felt that the 3-bit check was better overall because in this case we would rather detect it and not be able to correct it than to falsely conclude that there was an error there. So we consider the 3-bit to be more efficient than the 2-bit parity check because it uses the same number of additional bits in the transmission, but it can detect these errors which the 2-bit cannot. Thank you.